In fact, oh, it was a blimp. Sorry, it was not a hot air balloon. My bad. Yeah, I mean, it was like you're looking forward to a hot air balloon. Now it's a blimp. It's like, jeez. But we do have a lake. Lakes are good. All right, so for a man to cross a lake to a point directly east of his cabin, which I suppose we're to assume is on the edge of the lake, he must set a course 6 degrees south of due east so as to compensate for a current that flows to the northeast, 30 degrees north of due east. All right, so that's fun. If a man's boat travels 20 miles an hour in still water, so if there were no current whatsoever, that's how fast it would go. What is the rate of the current to the nearest integer? What is the resultant velocity of the boat? All right. I don't know. This guy's all messed up. So he's starting off at his cabin. He wants to get to a spot directly east of where he is. Right, east of his cabin. Here's a point directly east of his cabin. That's where he wants to go. So this should be the resultant. All right, all the forces at work here. This is the path that he should end up on. All right, he sets a course 6 degrees south of due east. So he's like, something like that. But then there's a current that's going 30 degrees north of due east. So it's going, so we got 30 degrees and 6 degrees south, but I'm going to make that a negative 6 degrees because if we're assuming the resultant is going in the 0 degree direction, that's 6 degrees clockwise, so making it a negative angle. All right. The man's boat travels 20 miles an hour in still water. All right. So the magnitude of his boat, and I'm going to call this vector B for boat, the magnitude of B is 20. All right, because that's the amount of propulsion the boat is offering. All right, whether it will actually amount to 20 miles an hour is a different story, but he's applying 20 miles an hour worth of force. All right, so that's what's going on there. Now, we need to know the rate of the current. We'll call that vector C for current. And C, the magnitude of it is completely unknown. All right, so we'll have to figure that out. And then we also need to know the resultant vector. All right. So we need some vectors. We need some information here. First thing we could figure out is that we have 20, if we're dealing with a boat, and we want to just kind of cut to the chase a little bit. For the boat, it's 20 multiplied by the direction vector, all right, which is negative 6 degrees. So cosine of negative 6 degrees, comma, the sine of negative 6 degrees. All right. Without the 20, we're talking unit vector, but by multiplying by its magnitude, we're scaling it up to also account for the speed of the boat, right? Or at least the speed that the boat is contributing to this whole fiasco. That looks like a K. That's C with an absolute value around it. Anyway, for the current, we don't know that information, except we do know the vector, but we don't know the magnitude of it. That's what we're looking for. So I would say C multiplied by the cosine of 30, comma, the sine of 30. And we can figure all that out in a minute. All right, those are unit circle values. But you look at this problem and you say, well, negative 6 is clearly not a unit circle value. 30, even though it is, I mean, obviously we're going to decimal form at some point here, nearest integer. So even though they're unit circle numbers, you're going to kick over a calculator at some point. So whether you want to do it now or later is up to you. All right, the resultant would be the sum of these two things. All right, so you could do the distributive property and get things going, or we can at least evaluate the resultant component and then see what's going on there, because you just make a little note for the result. I'll just say equals. I don't know what the resultant is. We'll call it R. But I do know that it's going to be the result of cosine 0 degrees, comma, sine of 0 degrees. So R comma 0. So for the boat, I really don't feel the need to go to decimal form just yet. I'll do it later. I can run through with the 20 and make it 20 cosine negative 6, 20 sine of negative 6. If you want to go coterminal on that, that's fine. It's just, it's dangerous. It's easy to screw things up if you make it the positive counterpart to the negative 6. So I say leave it. The calculator can handle it either way. For this one, maybe you do want to get those unit circle numbers involved. In which case, it's radical 3 over 2 times c. So c radical 3 over 2. And c over 2. All right. The sum of the two vectors, I can illustrate it here a little bit. Poorly, of course. I don't want you to get spoiled. Yeah, look at that parallelogram. That's disgusting. Not drawn to scale. So if we add our components together, the result should be the resultant. So 20 cosine negative 6. So we're essentially going to get a system of equations here. So 20 cosine negative 6. I'm going to go blue for those keeping score at home. 20 cosine negative 6 degrees plus c radical 3 over 2 should be equal to r. All right, equation with two variables, that's fun. The other one's not as bad. We have 20 sine negative 6 degrees plus c over 2. And that's going to be equal to 0. The second one is where we earn our, well, not, I was going to say earn our keep, but not really because it's easy enough to do. I'll put parentheses around here because it's starting to look a little nasty. So we can solve for the value of r here with our calculators. I'm just going to crunch it out real quick. I don't think we need to actually see it. We're working with degrees, so you'd have to be in degree mode. Oh, actually, you know what? Let me show you that real quick. So you don't have to change your mode on the calculator. I only learned about this when I became a teacher. And so we generally want to live in radian mode, but every now and then we have to do stuff in degrees. But I don't want to change it to degree mode just for like one or two problems because I'm going to forget to change it back and then screw up every problem after that. Right? So what I do is I leave it in radian mode. And when I need to figure out something like 20 times the sine of negative 6, I'll type in 20 sine of negative 6, but I'm going to put a degree symbol in. All right? The degree symbol you get by hitting second. See that angle menu right above apps? It's the one for converting polar to rectangular coordinates, same menu. So second, apps, pull up that degree symbol, and it'll treat whatever precedes it as a degree rather than a radian.
So you don't have to go back and forth.
Exactly.
For your next class and then fail test.
Exactly. So that's what it should be equal to, in theory.
It is.
Nice. So then I'm going to add that to both sides and double it. So times, no, just do negative 2. So our R value is about 4.2. Sorry, C value. And then after that, it's plugging and chugging. So I'd plug in the 4.2 for C in the second equation. 20 cosine negative 6 degrees. So second apps, option 1, plus, use my nifty fraction tool here, alpha y equals n over d. I'll take, so I want this answer. So I just hit the up arrow, hit enter on it, It'll pop it right in there. Because I want to at least have some degree of accuracy here.
How'd you get the that division sign with the two slides?
It's fun, right? Let me do it again. So, although I wish I didn't delete the cosine part because I didn't need to do that. So second half 0. So alpha, y equals, and you have the fraction menu. The first one is numerator over denominator. Select that. It's glorious. Then I just want to insert the previous answer. So I'm going to hit up arrow, hit enter. So I'll just pop that right in there.
Awesome.
Times √3. Hit the down arrow to get to the denominator, pop in a 2. Hit enter. And about 23.5. All right, and so these are speeds, miles per hour. All right, and none of these angles were right angles. So you're looking at something where, you know, we were able to do linear equations and some knowledge of trig. You know, and I'm not even talking about like advanced knowledge of trig, the basic stuff. SOHCAHTOA. We were able to figure out this stuff. So no law of sines, no law of cosines, sum of vectors, set up a couple of vector equations. There are some problems where I will show you the linear algebra approach. So row reduction techniques, matrix operations, so it's really all in the calculator, because I also don't want us to get bogged down with the algebra. I'm just debating of whether or not this is the opportunity to show it to you. Nah, one fancy calculator skill per night. How about that? So it ended up going due north, but she had to aim it 17 degrees west of due north. So let me establish what due north might look like. So she's shooting off at 17 degrees west of that. So I'll make this little angle here 17 degrees. And she's doing that at a rate of 45 miles an hour. So I'm going to let t be Tabitha's vector, but the magnitude of t would be 45. All right, completely fictitious problem because I honestly don't know how fast blimps go. So 45, I don't know if it's fast or slow. Seems kind of fast for a blimp, but you know, I'm not really sure. Because you know, I see like at stadiums, they're giving aerial views. They don't seem to be going fast, but I don't know if that's because they're choosing to go slow or if they're like incapable of going any faster. All right, so the wind is blowing 50 degrees east of due north. So we're looking at something like meh. So that magnitude would be 50. Oh, nope. Sorry. That's the degree measure. So that angle is 50 degrees east of due north. All right, so draw a diagram, we did that. We need to find the actual velocity of the wind-blown blimp. All right, so we're looking for the resultant vector. We're looking for, but I guess I'll call it B. This would be vector B. I mean, you can name them any way you want. But essentially, we're looking for the magnitude of B. And like I said, you can go back and forth. It doesn't matter. You can go with the single brackets or the double brackets like I'm doing here. Either way. Last problem, I went single brackets. This time I'm doing double brackets. So that's how consistent I am. So obviously you can be inconsistent also. All right, so we need to establish what's going on here. So we have Tabitha. I don't know her, so she doesn't get a capital. AKA, I forgot to draw it as a capital. So her magnitude is 45, so we're looking at 45 times the cosine of her angle and the sine of her angle, which is not 17 degrees, although it might seem that way. It's got to be the degree measure off of 0. So we're talking this third angle here. That would be the sum of 90 degrees and 17 more, so 107 degrees. All right, we can work that out in a minute, but let's take a look at the wind. More philosophical than anything else. We don't know the magnitude of the wind. I don't think so, unless I'm missing it. No, we just know the angle. All right, so the magnitude of the wind multiplied by the cosine of its angle. Now that angle here, I'll go black. We'll just draw it with an arrow. Well, it's 50 degrees east of due north. The complement of that would be 40 degrees. So we have a setup for both Tabitha and the wind. The resultant, that's probably, in terms of the setup, the easiest one to come up with, because you just make a note. Because really it's kind of like the absence of information, how much can you do? So we need the actual velocity of a wind-blown blimp, right? So that's completely unknown, so magnitude of the wind-blown blimp. But the angle itself is not bad. It's 90 degrees. I mean, it's more than not bad. It's wonderful. And because for the other ones, we have some angles, 107, 45, there's some things we can do with that, calculator-wise, but 90, that's a unit circle angle, but it's a nice unit circle angle, so no radicals in there. Zeros and ones are what we're going to be dealing with, right? So in terms of the diagram, we need to know that what we're dealing with is the sum of the two component vectors. So let me go orange. Bill's keeping score at home. So my diagram is always a joy, I suppose. This is supposed to be a parallelogram, right? So just suspend your disbelief. Oh, actually, you know what? I can at least make the attempt. And then the eraser probably is not going to work, so I can white it out. Just to make it look parallelogram-y. I mean, if you're not concerned with that, and don't worry about it. I mean, I'm not overly concerned with it. As long as you have some sort of way of knowing that the sum of Tabitha's information and the wind's information should be the resultant, right? So basically, I'm going to take the components and add them together and come up with a system of equations. So that's where the next step in this magical journey comes from. So may want to do a little intermediate step here. 45, that's part of the vector, cosine 107. Because a scalar can be distributed through a vector. Magnitude of W, cosine 40. This is a step that you could skip if you want, because you could go directly to your system, but I'm going to show it just so I can circle stuff and draw arrows and things like that. Or maybe you skip the previous step and jump right to this. It's entirely up to you. You can also combine some ideas, because this is the only one where we can actually simplify a little bit. Cosine of 90 is equal to 0. So this would become 0, comma, so 0, big space, comma, magnitude of b, because the sine of 90 is equal to 1. All right, so let's see if my highlighter looks reasonable tonight. Oh yeah, it looks like nothing on this screen. It's like yellowish on mine though. So it's like not much of a consolation, but
It's gonna load in like 10 minutes.
I'll just do it that way. Nice lag action. It's like I don't even know. Oh, I should put the pen back on now. But let me circle the other one. I'll circle that in blue highlighter. At least it's showing up. It's much more vibrant on my screen. Now I do have to put the marker back on. So all this stuff together is going to give us a system of equations because all of our x components should be equation worthy. The sum of the first two should equal the last one. So 45 cosine 107 plus w, magnitude of w, but that's a lot of syllables, so I'm just going to say w, cosine 40. And I'm also going to drop the degrees because it's extra effort that I'm unwilling to provide. All right, so that's our first equation. Our second equation would be 45 sine 107 plus magnitude of w sine 40 equals b. All right. So it's a system of equations. Not ideal. The previous one that we did had a system, and this one will work out too, had a system where you can solve for one of the variables and then plug in. But it's a little bit messier because we don't have those clean, so it's not ideal because we don't have those clean unit circle values. But the recommendation is to just go through the process without the calculator, leaving your answer in unsimplified trig function form, right? So don't go getting into decimal form because then you have rounding considerations that you'll have to deal with. Unless you use the store feature in your calculator to hang on to those most exact forms of the decimal. So what we're going to do is solve the first one. Let me circle it in highlighter again. I'm going to solve the first one for w. This time I'll actually do it in red because that's what I intended to do before. So we'd be looking at the magnitude of w is equal to negative 45 cosine 107 over the cosine of 40. All right, that can then replace, back to highlighter, and do that in blue, the w in the second equation. All right, so then we'd have 45 sine 107 really minus 45 cosine 40 cosine, I'm looking at the wrong thing. Cosine 107 sine of 40 over cosine of 40. And that would be equal to what we're looking for, essentially. It might be my overused word of the day, essentially. Didn't apply there. It's exactly what we're looking for. Right? It just it doesn't look very much like the form that we would want our answer in because it's supposed to be, I believe, in miles per hour. So we have to crank this out. Little recommendation. It's something very subtle. Some of you already thought to do it. The angles are the same, so why not make this tangent 40 a little less to type into your calculator, right? So not a requirement because you can go either way with it. Still get the right answer. I'm going to pop it into degree mode because we are working with degrees. And then 45 times the sine of 107, then minus 45 cosine 107 times the tangent of 40. Just again, so I can type less stuff in. And then hopefully we get something that makes sense. Otherwise, I do that stupid stare at the screen while I try to figure out what went wrong. Or try to make up a excuse for why I got the wrong answer. All right, ready? All right, okay. I don't know if it's absurd or not. I'll look at the context in a second, but we do have an answer that is positive and not absurdly large. So it's not like traveling faster than the speed of light or anything like that. So, all right, we're in a good spot, at least for the time being. So 54.1, I don't know anything about rounding in this context. I'll look at that in a second also. All right, I'm not big on giving rounding instructions wholesale. You know, it doesn't always seem to make sense. I do it problem by problem. If rounding applies in a particular situation, oh, okay, so hold on. There we go. If rounding applies in a particular situation, I'll tell you question by question. It's not going to be generally round everything to the nearest 10,000th because, you know, that rounding instruction might make sense for one type of problem but not for another. If anybody's taking the stack course, you know what I'm talking about. All right. So, so yeah, 54.1, 54 maybe, right? Because the skill here is that I'm assessing is not your ability to round. Nearest integer, there it is. So that would be approximately 54 MIFs. Miles per hour, as Kelly Bundy would say. Old TV show reference. Yeah, it's supposed to be how... okay, so it looks like the blimp was being helped by the wind, and that seems to be supported by the diagram, because she aimed it west of north. The wind was blowing east of north at some velocity that I'm unaware of, and so are you. But it seemed to, well, it's blowing in the direction that the blimp was going somewhat. So there is some component, keyword there is some component of vector W that's acting in the direction of vector B. All right, so it's acting in support of her journey, or actually in the resulting in the direction of vector B, but it's supporting her in her direction vector T in this particular case. All right, so a lot of fun stuff in that one. Good problem. It's a new take on an old problem. You know, so back in algebra, trig, things like that, you would use the law of cosines for a question like this. Now we use vector addition, right? But as you can see, the concept of the trig is still embedded in there because not everything is a right angle, right? But I tend to throw a bone here and there, so you could expect a right angle. Just don't expect them all to be right angles, obviously. All right. So the next one is a good problem too. A 50-pound weight is hung by a cable so that the two portions of the cable make angles of 30 degrees and 60 degrees respectively with the horizontal. Find the magnitudes of the forces of tension T1 and T2 in the cables if the resultant force acting on the object is 0. Ah, dang it, I meant to change that. I don't like writing the subscripts over and over again. It's annoying. It's perfectly okay to do it. It's just I had them on my diagram originally, and I changed my diagram to give somebody typo bonus, but I never changed it in the problem. All right, so U and V is what I would like them to be. So if somebody wants to claim that for a bonus, So U and V.
When it says respectively, does it just move from right to left? Because nothing's labeled on the diagram.
Yeah, that's also something I changed. So we'll change respectively from, we'll change it from respectively
And
to,
you just added U and V on the diagram.
yeah, I'll take that as another typo. So change T1 and T2 in the problem, add U and V to diagram, two separate typo opportunities. Yeah. And that should square things away. And as always, I just got to make sure I answer the question based on the phrasing of my own problem. So we have 50 pound weight, that's obvious. 30 degrees and 60 degrees, so going from left to right, the magnitudes of U and V. So 30 degrees, 60 degrees. Calling one of them U and the other one V. Since I got to find them both, doesn't matter which is which, as long as it's properly labeled. I might as well just label the angles too, so third typo. A little something for everyone. Or actually, at most 3 people, so not everyone. The opposite. So anyway, we need to set this one up, but they seem to be giving us the angles in a place where we would not necessarily want those angles, right? So I need a horizontal, so let me do that. I'm going to use my line draw tool here. Okay, I kind of went overboard with that. All right, that's a little bit better. All right, a little geometry action. If 2 parallel lines are cut by a transversal, then the if 2 parallel lines are cut by a transversal, then the
Interior is opposite.
not adjacent, another word that starts with A. Alternate interior angles are
Same.
the same, but the geometry word, not that it matters, but the fun geometry word that means the same, congruent, yeah. So that was stuck in my brain, not initially.
That's not how it.
No, that's wrong.
Isn't it supposed
Oh.
to be the other way
It's supposed to be 30 on each.
I was trying to tell a story and you scared me. I freaked out and I made a mistake. All right, I'll work on that in a second. But anyway, I'll do the story part. So 9th grade, Mr. DeCiccio, Mahopac High School. He went around the room. There's like 25 people in class. So he had us go through all the geometry proof theorems, at least the parallel line ones, one at a time, person by person. So it like echoed in my brain like for the rest of my life after that. It was, and fortunately I wasn't one of the first few in the class because like you hear it over and over again. Yeah, exactly. And so it's like, wait a minute, nah, it's not gonna happen. Wait, oh, this is really gonna happen. Okay, I got like 5 people to figure out what I'm supposed to say, and then I still kind of put it off, and then 2 people ahead of me, I started actively listening. I'm like, all right, better pick this up now. 2 parallel lines are cut by a transversal, alternate interior angles are congruent. Okay, got it. And then the next person reinforced it, then I said it, and then the next 4 people afterwards said it. But then he moved on to corresponding angles are congruent. Vertical angles are congruent. And it was like, that was the whole class period. And it was like, I was thinking to myself at the time, like, you could probably just tell us to go home and study this. It's an honors math class. But based on his years of experience, I'm guessing, and now that I'm kind of in his shoes, I'm guessing that that just didn't work, you know? So, like, for example, if I didn't have him for trig, but if he had said, go home and study the unit circle, probably wouldn't have happened. Right? My teacher for trig didn't do that. You know, we didn't do anything fun in class, and it was like, all right, well, you should probably know this unit circle and then go from there. But I would imagine that if we had to go around the class and state all the angles, then go around the class and state all of the coordinates and angles, degrees, radians, then coordinates. First off, the idea of speaking in class, it strikes fear into the heart of some people. So it's like, whoa, hold on, pal, let's not do that. I know it worked for you. Like 2 theorems in math, but like we get the point. We're going to study the unit circle. But yeah, like that kind of stuff, it never went away. And I haven't taught geometry in like 10 years, and it's still there. It's crazy. So, okay, so I'll try to draw this picture correctly now. So 30's over here, because that's what an alternate interior angle is. 60 degrees is over here. Yeah, he's a great teacher. I love that guy.
Scarred you.
Yeah.
But it was fine, right?
No, that was the one standout moment in terms of making us memorize something. Everything else in that course was a ride. He just made everything so much fun. Like it's a gift that I'll never have, but I try.
When we're solving stuff like this, would we use the physics-based thing, or would we use the 30, or would we go the full 180 around?
We're gonna go, and then,
Okay.
and then of course, we don't want to forget about this guy. Got another one. All right, so we got 60, we got 150, and then we have 270. All right, so we have U, V, and, well, why not, right? Call it W. All right, the most popular names for vectors. Also, W could be for a weight, I suppose. So we're talking magnitudes are unknown, yeah? So the magnitude of U, and I'll just cut to the chase on this one, cosine of 150. Magnitude of U, sine of $1.50. Then V, magnitude still unknown, but now that's 30 degrees, 60 degrees. Cosine 60. W is the good one. There's always the way these problems are kind of selected. You always try to throw a nice one in there. Like I said, I'll throw you a 90. All right, so 270 is a 90-degree movement in some direction. So we know that the magnitude of W is equal to 50. So we're going to say 50 cosine of 270, 50 times the sinus of 270. So we have all those vectors established, and that's all wonderful stuff. Just got to kind of know what to do with them. If you just follow the trend from the last couple of problems, you might say, add the first two to give you the third one. And, you might consider that to be a reasonable approach without even considering the physics of it. And it's like, well, just add them because that's what we did the last couple of times. But in this case, we're going to do it because in order for us to have equilibrium, we would need the tensions placed on these two wires, I think they were, cables, to balance out the 50 pounds that are acting in the opposite direction. Right? So there has to be 50 pounds worth of tension on these two cables in order to keep it in place. Right? If there was anything less than 50 pounds worth of tension, then the cables would snap. If there's anything more than it, well, and it's overkill. Because you could have cables that are able to support thousands of pounds. If you only put a 50-pound weight on it, then it's all right, cool. It's like I don't know, trying to reel in like a trout with the same fishing line that you would use for like sea bass. Like if anybody understands fishing references. So It's just overkill. But it doesn't mean that it's going to start floating necessarily, because gravity is still a thing.
Wouldn't we want to do it based on the cosine times 90 because it's equal to the negative of gravity?
So you have a choice. You can go with a negative magnitude with a 90-degree angle, or if you go with the cosine 270 sine of 270, you're naturally going to get the negative out of that. So all roads lead to Rome in this case. So that's our license. That just arbitrarily decide to change from cosines to sines. Just zero, because the cosine of 270 is in fact 0. So cosine of 150, I might as well just kind of clean this up a little bit while I'm here. Cosine of 150 is equal to? We all didn't get around to that square root of, what do we say? Square root of 3 over 2. Some of us got around to the bonus challenge, but not everybody. If you do, it might pay off. Cosine 60.
What is the bonus challenge?
Day of the test.
Square root 2 over 2.
1 half.
No,
1
1 half.
half.
That's
Oh, wait, no.
A week from tonight. So the thing that I like most about that bonus challenge is that not only do you have to know what the values are, you have to know placement, you know, and in any order. So it isn't just a matter of memorizing, well, I'll write this, then I'll write that, then I'll write that. It's like you need to know.
There's somebody there that did it in like 53 seconds.
I know, I saw that. I was like, I can't even do it that fast. This is great. I think it's like the person who created it, created the unit circle.
Right.
Like they traveled forward in time. And then 50, negative 50. All right, so we'll need the sine of 150. Think I heard somebody thinking. Yeah, negative 1 half. And the sine of 60. Boom.
Would it be negative 1 half?
Wait, why
Would
is
be
it negative
positive?
1 half? It's sine's positive.
It is positive. I thought you said negative.
I said 1 half.
Yeah.
And it's negative
Negative 3 over
cosine.
2, 1 half, yeah.
And negative cosine.
But you got it.
Yeah.
Okay, so we can solve this system any way we want, but I'm going to show you a different way because you know how to solve systems algebraically, and it's a wonderful approach. It's very doable. It's just moving forward, you're going to want shortcuts for getting the solutions to systems of equations. Right? In Calc 2, we did it a little bit with partial fractions. So it's a matrix approach that we're going to use, and I'll show you. You know, it's going to give you decimal answers, but in this context, decimal answers are expected, so that's fine. All right. So what we're going to do is write just the coefficients, and without taking a linear algebra course, you're not really going to get a true sense of why this is going to work the way it does. But what we're going to do is create a matrix, a coefficient matrix, for each of the two variables. So we have negative radical 3 over 2 and 1 half. We also have 1 half and a positive radical 3 over 2. Those are the coefficients. They're equal to 0 and negative 50 respectively. We could, but we're going to let the calculator do all the work.
Ah,
right? That's the thing.
Could we have done Kramer's rule for this as well?
You could.
Yeah.
You could.
Because I was looking at it, you can just substitute the coefficient and like the zero. Like say if you're trying to find u, the zero you put in for like the first column, like the 0 and the -50.
Right.
And then you would multiply across and then divide it by whatever you have.
The
there.
determinant for the other part. Yep, exactly. So Kramer's rule will take care of it. What we're going to do is use row reduction, reduce row echelon form, because that's going to, the calculator has that built in. It does it for you all in one shot. All right, so we're going to use the ref feature on our calculator. So ref, and that's in the matrix menu. So I'm going to show you how to put this in if you don't already know, and then I'll show you what you actually hit to get a row reduced form. You can solve this stuff out algebraically without a problem. This particular question, the ones that preceded it, no problem whatsoever. It takes a little bit longer for this one than the previous ones. You'll get it, it's perfectly fine. But then when we go into 3 dimensions and you have to solve a system of equations in 3 variables, it becomes time consuming and we don't want to do that. All right, so that's why I'm showing you this way. All right, so to the calculator. Actually looking for a calculator for some reason. So you're going to hit second and this x -1 key, inverse key, which is right next to sign. Brings up the matrix. And it just gives you names. When I was a student, I never got past this menu because I was like, I don't know any of these names. So I didn't know what to do with it. In fact, you don't do anything with it yet. You go to edit. And select matrix A. You can take whatever matrix you want, but A is as good as any others. So select matrix A. What we have here, it's an augmented matrix because we're including the solutions. A 2x3 matrix, all right, 2 rows and 3 columns. So 2, enter, 3, enter. In the calculator, it forms the fields, or the matrix fields, based on the dimensions that you put in. So you write out your matrix on paper, and then you put in accidentally 3x2, and it doesn't look like what you wrote on paper, and you're like, okay, I got it in backwards. That should be an easy enough fix. So what we're going to do is type in the values that we put in the augmented matrix. So negative square root of 3 over 2. Hitting enter slides you to the right. Then back now. Then 0.5. It's converting automatically to decimal form. After you complete the first row, hit enter, it brings you to the second row, and you do the same thing again. So 0.5, positive radical 3 over 2. And negative 50. All right, so all those entries go in. We'll quit out of here. So again, we did, I'll just jot this down on my tablet. So we did second, we had that x -1 key, we went to edit. So quit, second mode. Go back into the matrix editor, not the matrix editor, the matrix menu. So second x -1 key. Now you want to go, and you could actually see under names for A, it says, bless you, 2x3. That's because there is a 2x3 matrix stored in there. Ideally, it's the correct one. We'll find that out in a minute. But if we slide over to math and scroll down, like keep going past 7, it'll be option B. You're looking for the one that says ref. All right, not ref. You can work with ref, but ref is the one that you want. That stands for reduced row echelon form. Basically, without getting into the linear algebra of it too much, it's telling us, or it's giving us a simplified form of the coefficients that make up our system of equations. All right, so I'm going to select this function. Then I'm going to call back to matrix A. So second inverse key, so matrix, select matrix A, and then hit enter. All right, so you want R ref of matrix A. Once you hit enter, it gives you that stuff. Maybe it's math frackable. Give it a shot. Sometimes it is.
No.
It kind of is, but not in a meaningful way. Right? I mean, I was hoping for like -4/3 or something. You know, like this is not what I have in mind. So I'd rather have the decimal. All right. So I'm going to write it out. We have 1, 0, 0, 1, -25, a shockingly clean answer, and about -43.3. All right, so let me go back to this. So now we have that, and we just have to think about what it means. All right, so I started off with -√3/2 magnitude of u, 1/2 magnitude of v. Those served as the coefficients of whatever our system was. That made up our entire first row. Right? The coefficients of our second equation made up our entire second row. Right? So what we're looking at here is a coefficient of 1 for the magnitude of u. So I'll write a 1 there, plus a coefficient of 0 times the magnitude of v is equal to -25. All right, because what it did was it simplified our equations in such a way that one of the variables has a coefficient of 0, which allows it to zero out. The other one has a coefficient of 1. So it makes up what we call the identity matrix, not that you need to know that. All right, but it boils down to the idea that we have the magnitude of u being equal to -25. All right, then we have the magnitude of v, because the same idea is going to hold for the second equation. We have coefficients of 0 and 1. The magnitude of v would be -43.3. So we have to think about contextually what we're dealing with here, because we established, or at least I did, that the magnitude of the weight was 50 pounds. All right, so we established the positive direction as being downward. All right, so these are just simply in the opposite of that direction. But all we need are the absolutes of these. So we would conclude that u would be 25 pounds. I think they were pounds. And v would be about 43.3 pounds.
Do we care that they're in the wrong unit from the problem?
The wrong what?
The problem wants it in force units, and we're answering in mass units.
A pound is a force.
Yeah.
Is it a force? I
Mhm.
thought it
Because it's either pound mass or pound force.
Okay.
If we were giving it to us in kilograms, we'd have to solve for force.
Right, yeah, we'd have to do the MA part of
I
that.
thought it had different notation if it was.
For the English, it's either pound mass or pound force.
Isn't the pound mass called slugs or something?
Yes.
Geogebra? Yeah, next week we're going to talk about the first technology assignment, which is going to be a GeoGebra-based activity. And 3D, you start to really see the value of GeoGebra for that. Because there are some things where, like coordinates, once you get a sense of it, being able to plot them in 3D, it's not too bad. But when you see a function of two variables, which you've worked with before in calculus, in Calc 1, but the idea that it actually represents a figure in 3 space, it can be alarming. And unfortunately, the calculator doesn't really do much for you there. Right? So GeoGebra helps you to get a sense of what these things look like, so that when you go into a test, you're not blindsided by a function. That was the whole thing. It's like, I mean, I could go through all the motions when I was a student, but then when it came to actually really, truly understanding, I don't think I ever really truly understood what was going on until all of this technology was invented, which was like after I was a student, which kind of sucked. But then again, Google didn't even really exist in its current form then, so I mean, I can't really complain too much. So the point, when you're plotting a coordinate in 3 dimensions, or 3 space as we call it, you have 3 components. You have an x-axis, a y-axis, but you also have a z-axis. All right, so when you think about a 3-dimensional figure, there's length, width, and there's also height. All right, so this is incorporating potentially height if you're talking about linear distances, but it could be anything. All right, so at this point, we're just talking about plotting. This could actually be an Algebra 1 type of question, because it's really just like, all right, when you see this number, you move this way. When you see that number, you move that way. All right, it's as simple as that. All right, the first value in an ordered triple is the x value. Second value is the y value. And you guessed it, the z value. All right, so when you think of it that way, it's not too bad. But what you do is a little bit different, because we're graphing 3-dimensional objects on a 2-dimensional plane. I mean, okay, it looks like it's a 3-dimensional plane, but the paper that you are writing on is a 2-dimensional plane. So everything is a perspective drawing. So we have to know the rules of the perspective, right? So if you think about the idea that what might seem like a rectangle, or like rectangular form, is actually a parallelogram, that tends to help, right? Although, since I can't draw a parallelogram, that might be problematic. The x value is just the number of steps along the x-axis. The x-axis comes out of the page in your direction, right? So, well, perfectly in my direction, but maybe you have to kind of shift your body a little bit to really see. But if it's positive, it's coming towards you. If it's a negative x value, it's going away from you. You'll notice as you go through the packet, you'll see problems online. Nobody labels the negatives, all right? Because what happens is the graph gets too busy when you do that. So they only label the positives and then just ballpark the negatives. All right, so what I'm going to do is I'm just going to go out 1 unit in the x direction. This is not my coordinate. I'm just using it kind of as a placeholder. All right, so I'm just kind of like identifying that location. I should have done it in black. Color code. Come on, man. Jeez, this guy. All right, so there's my x. Y is -2, so I'm going to go -2 units in the y direction. So positive y is to the right, negative y would be to the left. I need to go 2 units. So just getting a sense of what 2 looks like, I'm going to go 2 in the opposite direction. So there's 2. All right, so this is where the perspective comes into play. What I'm going to do is create a parallelogram using the sides connecting the points to the origin and the opposite sides. Just as you would if it were a vector kind of thing, like a resultant vector situation. All right, so this point here, that's actually 1, -2, 0. All right. If you're living in the z = 0 plane, you're in the ordinary Cartesian plane, x-y axis. That's Earth 1, right? That's the case where everything is as it always was. It isn't until you shift up in the z dimension that you're displacing out of the ordinary plane. So that's what we need to do here. We need to take 3 steps in the z direction. So what we do is we figure out what 3 steps looks like. Maybe use the side of an index card, piece of paper or something like that. Get a sense of what 3 steps looks like. And then just slide on over. Mark that off. And then plot the point in space. All right, so this is what 3 looks like. I am not going to successfully be able to do, yep, okay. It still is not something I'm capable of doing. That distance is what I need to have put over here. So like right about meh. Maybe a little bit more meh. All right, so this point here is 1, -2, 3.
That's 2. No, it's the perspective of the.
Yeah, so it's going to look a little lower because it's been shifted downward, but it is going to be 3. Well, or at least the best I can draw.
Should be 3.
Shift it
This
backwards.
distance.
Just write a D next to the line that goes 3, and then just.
Oh,
Shift
I
it
see.
towards us.
I see.
Yeah, just label it with something.
Just label it, so.
I'll just do the old geometry labeling. Congruent. Nah, that fixed everything. It's great. Life. All right.
To scale.
And it's completely to scale. You know, it's a work of art. It looks better as I zoom out, of course. But yeah, that's how you plot a point. Now, you could already see how problematic it would be to plot an entire surface, which is made up of infinitely many points. How would you do that? How would you draw even a sphere in 3 dimensions? Right? It's not easily done. You know, there's like a lot of framework going into it, and really that's why I push Geogebra a lot, because it does give you a true sense of what the images should look like without you having to like really destroy yourself trying to do. When I took Calc 3, I'll tell you that I would say like half the course, or at least it felt like half the course, was just drawing this stuff. Maybe you would like that more. I don't know. Well, you wouldn't know that yet. But you know, some applications here. Write an equation of a plane passing through the point 3, 11, 7. That's parallel to the YZ plane. All right, so you got to start thinking about what these planes would boil down to. So if I'm going to just do a freehand on this, I have Y, I have X, and I have Z. So do it in any order you want, as long as you have them labeled properly. The XY plane, you could kind of think of that as the base, or the horizontal plane, right? That's the case where Z is equal to 0. Anything above or below that would be where Z is equal to 1, -1, -30, it doesn't matter. YZ would be this panel for any possible value of X. So it would be more of a vertical plane. And then the other possibility would be XZ, which would be this panel, which would be vertical but kind of the corner. So if you really want to get a true sense of what the X, Y, Z planes look like, it's right there. Right. So here's X, here's Y, and here's Z. Right? So XY plane, YZ plane, XZ plane.
Why don't we draw Z as going up, like with the direction Y usually goes to on a 2D graph?
Well, because Z typically, more often than not, represents the height of a figure. So it's really just trying to visually manifest that idea. And most of the time when we're dealing with X and Y planes, we look at X versus Y in the way that we do, because, well, first off, because somebody decided that that's the way we should do it, and that kind of stinks. I don't like it when that happens. But also, what we're really doing is just trying to kind of restrict our variables. So if you're defining something in terms of 2 variables, like a physical motion, odds are if the object's in flight, for example, the y-axis is going to represent the height of that object, whereas the x-axis might represent the the horizontal movement, but that's all along one plane, right? Because that's the thing. When you're dealing with those classic projectile motion problems, you know, like the thing thrown up in the air, find the max height, the ones that we all love, it's all on a single z plane, right? It's just your x, y, z plane has been juxtaposed, so basically flipped on its side, so it's really xz as your base with the y going up, just so that the textbooks and math teachers could take advantage of x versus y, with the implied aspect being that there is a z plane out there that would have some impact. But what happens is all those problems have the little caveat that the object's being thrown up in the air and then coming down, it's not wiggling throughout the approach. There's no curveballs, right? So the object goes in a straight line path And I don't mean like the curve itself is straight line, but it's on a plane that is the straight line base, right? So it's shooting up in the air, but living on the same plane, as opposed to like a pitcher in baseball, where they're not living in the same plane. They actually change their planes. The better pitchers do change their planes. So a curveball would start on a plane, then kick out into a different Z plane, and then come back in, possibly going through many more planes. Right? So all of that stuff comes into play here, but you never could have done it before. Right? So really interesting stuff, and it's finally an opportunity for you to explore physical phenomena in a meaningful way, because it's like, yeah, I mean, I could throw stuff in the air, but to expect it to not have any lateral movement, that's unrealistic. Right? So when we're talking about writing the equation of a plane, though, that's not bad, because if it's parallel to the YZ plane, you're just thinking about that. Here's YZ. That means that it's living on some constant value of X. All right? So all we're really saying is that it's got to be on the X equals 3 plane. Because if it's living on some X plane, aka it's parallel to the YZ plane, but it also has to go through the X value of 3. It must be on the plane X equals 3. Now, how could I define a plane X equals 3? That doesn't seem to make any sense. X equals 3 isn't that a vertical line? But X equals 3 in a two-dimensional system means X is 3 for all values of Y. All right, so that allows it to be a vertical line. In 3 dimensions, X equals 3 for all values of Y and for all values of Z. So now it expanded to be the equation of a plane. All right, so it's little ideas like this, the transformation between two-dimensional systems and three-dimensional systems, which is where your mind needs to kind of take it. Now, I mean, there's rules here. You can read the rules. Rules are helpful, but the visual representation is where it's at. Go on Geogebra, take some time, plot some points. There's a 3-dimensional calculator. Plot some points, type in some equations, see what's going on. It does pay off for you. All right, so that's where we're going to leave it, obviously, and we'll pick up. Kinda, definitely stop there, by definition. All right, so according to my notes, we did number 1, but we didn't do number 2. But it's easy enough because I mean we have our relationships here. But if you're visualizing what a plane would look like in space or any kind of points in space, what you're doing, at least in the simple cases, without getting into cross product and dot product, which we'll get to later, we're just looking for consistency in a component to whatever coordinate we're looking at. So the X values are varying, the Y values are staying consistent, the Z values are varying. So what this would tell us is that regardless of what X and Z are, Y is always going to be equal to -2. So this would actually have to live on the plane Y equals -2, regardless of what all these other rules are. Because if you were to plot these points, they would be all over the place in terms of X and Z.
But they share one plane.
Yeah, they have to be on that same plane for Y, otherwise they would have different Y values. Right? Now, the distance formula, that actually applies. It's a cool little development. It applies no matter what dimension you're in. Just you throw on whatever the dimension is. So x2 minus x1 squared plus y2 minus y1 squared, that's the two-dimensional component of the distance formula. Throw in a z component, and now you have a three-dimensional distance formula, fully functional. All right. So what we get from that, and I'll show you an example real quickly. I wanted to actually derive it because it's easy. I mean, you don't need me to do subtraction for you. I wanted to show you why it worked. This is not supposed to be here. All right. Well, whatever. I'm just gonna do what I want to do, and then we'll solve the problem at some point. This little piece here. It's a perspective drawing, or at least an attempt at one, but that would be a right triangle into space. All right. So it has an x component, a y component, and a hypotenuse. So, you know, it's just a little different from what you would expect. You'd have to kind of look at it this way, you know, straight outward, in order to have that x-axis, y-axis feel, with z kind of coming out the paper at you if you're looking down. So basically, you'd have to stand where I'm standing, looking the way I'm looking, in order to see it as an x-axis, y-axis with the z coming out of the paper. But anyway, there is an x dimension. There is a y dimension. All right, we could just call it that, but really it's a change in x values. So I'm going to throw a little delta there. And I'm going to throw a little delta there too. All right, so delta x and delta y. All right, so the hypotenuse, that hypotenuse would be, you know, we could define it as a new variable, or we could just say what it would be algebraically. It's the sum of the squares as a root. So it's the square root of delta x squared plus delta y squared. All right. Now that length also serves as a leg to a different right triangle. All right. So that length, square root of x squared, or delta x squared plus delta y squared, that has one leg of the triangle. The other leg would be delta z. It's some change in z. All right. If we call this side d, we have a Pythagorean relationship. I could say delta z squared, that's in blue, plus the square root of delta x squared plus delta y squared would be equal to d squared. Square each part, and you get delta z squared plus delta x squared plus delta y squared equals d squared. Solve for d and move some things around, and you get this. Which is the formula above, just the one above is a little bit more explicit.
And you can do that for all dimensions?
Any dimension, yeah. So 10 dimensions. I don't know what letter in the alphabet we'd be up to, but you can keep going, yeah. So if I need to find the distance between, and obviously in order to solve a simple problem like find the distance between 2 points, you wouldn't necessarily have to derive the entire formula. But it's nice to know, and especially since I'm going to ask you to prove some formulas or a formula on the test, it's definitely a good idea to become more and more familiar with this stuff as time goes on. So the difference between the x values squared, 9. Difference between the y values squared, 25. And difference between the z's squared would be 4. So what do we got, 36? Nah, I wanted it to be 36. Yeah. Fallacy of the preconceived notion.
Are there Pythagorean, I guess, quadruples? Okay.
I was gonna say, isn't that like a multi-dimensional Pythagorean theorem?
Yeah, it exactly is that. So there are triples that work. It's just they're never as nice, or as, when I say nice, I mean as commonplace as your 3, 4, 5, the 5, 12, 13, 8, 15, 17. So I don't even bother with them because it doesn't save that much time to know them. I had fun though. That's all that matters. They're like, oh, that dude's gonna fall again. So, anyway, equation of a sphere. is defined based on the radius of whatever the sphere is, or what the dimensions of the sphere are. So it works the same way as a circle. Right? The circle in general is Pythagorean in nature. It's just infinitely many right triangles going around. Right? So it's the same idea as a sphere. It's just really omnidirectional. It's going everywhere. So what we want to do here, if we're going to write this standard equation of a sphere, which has a very circular feel to it, it's going to be essentially to find the radius, because once you find the center, if you know the radius, then you know the equation of the sphere. Right? So our first challenge would be, I suppose, to find the midpoint. Oh, it's at the center. Sorry, I'm thinking of the wrong problem. They gave us the center. So we're already good there. Oh, that is not my marker. So we just need to find the length of the radius, so the distance, again, the difference between corresponding values squared. Right, so 11 squared, 121, plus 10 squared, 4 squared, 16, and 6 squared, 36. 52. Is that root 173? Yeah? Ugh. All right, well, it's going to get squared anyway. Oh, the difference between the x values, 10 minus negative 1.
Oh, okay.
Shockingly, I didn't screw that part up, but I almost screwed up the 7 minus 3, which is obviously not equal to 10, but somehow I wanted to make it equal to 10. All right, so this is our radius. We have the center again, so it's x minus whatever the x value of the center would be, so x minus 10 squared plus y minus 7 squared plus z minus 4 squared would be equal to 173. All right, so not something that you could verify on your calculator, but something you could verify on Geogebra. You could, I think, do it on Desmos also, although I have trouble with three-dimensional stuff on Desmos. It's, for me, easier to do it on Geogebra, and that's only because there's a dedicated app it's specifically designed for 3 dimensions. So at least in the early goings, you may want to consider just checking your work on Geogebra. You know, it doesn't have to be on a computer, because the website on your phone works pretty well, or at least it works as well as the computer. I mean, sometimes, I got like fat fingers, so sometimes it's a little iffy, but you know, you can kind of make your way around it. So x minus 10 squared plus y minus 7 squared plus z minus 4 squared equals $1.73. Big blur. Not really though, because we just zoom out some.
The 3D graph thing, that's only online, right? That's not on the app.
It's not on the app, so you have to go to the website. Let's get rid of the plane. I don't need that. It's bothering me. My axes, I thought they would be here, but they don't seem to be showing up. But we can live with that also.
And you need the plane as well.
You're gonna need the plane.
Well, I'm gonna show a different way of verifying it. I just want to change some settings though, because sometimes the colors are a little too dark. I like this one. This shows up pretty nice, like maybe even that one. You know, it's a little brighter. So they gave us a point, -1, 3, -2. And as long as it shows up on the surface of the sphere, I'm pretty satisfied that it didn't just screw this whole thing up. So, and it does. And you can plot the center too, but I'm pretty confident that it didn't botch it. So, but you know, just for the sake of consistency, that looks like the center, and that looks like it's on the surface. All right, so. The other thing I like about GeoGebra is if you know some math words, so does it. So just start typing the math word that you know, and odds are there's a function related to it. So I wanted to draw a line segment. I could have drawn a line, but also, you know, the emphasis on vocabulary for a math teacher is probably a little bit more than maybe a student would emphasize. So you might say line, where I say segment. Right? So I automatically think segment. Line is infinite, it goes forever. If I only wanted to connect 2 points, I would want just a segment. Right? That looks like a radius. That looks like a segment connecting a point on the surface and the radius of the circle itself. And of course I can make it like rotate and stuff. Yeah, it was just too close in, I guess. You know, just kind of get it moving. I mean, that doesn't do anything in terms of giving us a better answer. It just makes it look cool. So.
Screensaver.
Yeah, exactly. What is it? Screencast-O-Matic? I think that's what it's called. It's like a cheap version. Like it's a free version anyway. That it'll allow you to record your screen in like short bursts. So I'm sure you probably know the better versions of that. Anyway, number 2 is basically the same idea. That's what I was alluding to in the previous question where I said, oh, let's find the midpoint. But in this case, we didn't know the center. If we know that these are 2 points on the circumference of the sphere, so on the outer surface of the sphere, specifically forming the diameter of the sphere, it's important that we know that it does go through the center, because if it was some other line segment connecting 2 points on the surface of the sphere, then there's no guarantee that the midpoint of that would give you the center of the sphere. It would give you the center of a sphere, just not the one you're looking for. But in this case, you could find the midpoint and then find the distance from that midpoint to one of the 2 points, P or Q, and that'll give you the length of the radius, and then you can go from there. Okay, so I'll pop a little star on that bad boy, now that I flat out told you how to do it. And it's at the 8:15 mark in this video, if you're wondering later on how to do it. I know we went over it in class. But that would, of course, require you to write down that it was at the 8:15 mark. All right, vectors in space. I used to have much more elaborate notes related to this topic because I thought it was necessary. Then I taught the course a few times, and I realized it's probably completely unnecessary because all we're doing is rehashing everything in 2 space, just adding a 3rd dimension to it.
You mentioned at one point when we were talking about the distance formula. You want us to do proofs during the test. Like, what would you want us to do? Like exactly what you showed before, how you develop the equation?
Yes. So, if you want a very good sense of what would be expected of you, this is the part where it seamlessly transitions from screen to screen, and I don't have to wait.
No signal.
There it is.
No signal. Are you recording this?
I am, yeah. The extra practice review section on my website, if you go to the review problem set, well, this is the answer key of it, but whoops, there was a problem loading more pages because the internet here sucks. Asgard. Yeah, because that just brings you to another page. All right, well, you'll just have to take my word for it. If you scroll down, like all the way to the end, you'll see all of the different possibilities of things I could ask you to prove. And then from those, oh, here we go. Just a little refresh action. Yeah, we're getting there. Getting there. Possible proofs, derivations. So any of these are possible. I'm only going to choose one to put on the test. All right. So if you know them all, you're good. People have rolled the dice in the past and only known like 2 or 3 of them, and just hoped that it was going to be one of those 2 or 3 of them. And sometimes works, sometimes doesn't.
When are we gonna stop the number 3?
The end of class on Tuesday.
Like, is it gonna be another 3 pages, 4 pages?
A bunch more pages. Yeah. Yeah, we got a little ways to go. So all of this stuff is consistent from vectors in 2 space. So vectors in 3 space, vectors in 10 space, it all works the same way. All right, so it's just, it would be rehashing the old stuff. Even unit vectors, except you have a 3rd component as opposed to 2 components. All right, so it's easy enough. So the dot product, the plot thickens. So we're going to learn about the dot product, and next class we'll do cross product, and that's where the unit will end. But and so little applications of the cross product. There's also calculator shortcuts for some of this stuff. Sometimes it's not really as worth it as you might think. You know, some other topics it's like, oh, thank God we have these calculator shortcuts. And then other topics it's like, I think maybe the calculator shortcut takes more work than doing it out by hand. So yeah, well, it's risk reward, I guess. But anyway, the dot product is really just the sum of the product of the corresponding components from 2 vectors. All right, and we'll get into what it all means as we go forward, but for now it's just a skill. All right, so if I want the dot product of u and v, I'm going to take the corresponding parts, multiply them, and then add the results. So we're looking at -3 plus 15 plus 0, so the dot product is equal to 12. All right. Again, what is the dot product? We're getting there. Learn the skill first, then we talk about why it's useful. Concept of orthogonality, we'll get to that, but this is going to lead into that concept. If you have any idea what orthogonal means, this is going to support that idea. Anyway, the scalar product, if we're talking about a scalar product between 2 vectors, then we're talking about a dot product. All right, so scalar product involving 2 vectors, or if they say a vector scalar product, then you're talking about a dot product. All right, they mean the same thing, it's just the verbiage is slightly different. All right, the IJK notation, it just takes the place of the vector notation. And so if you want, just for consistency, you might consider writing P as 10, -4, 7, and Q as -2, 1, 6. In order to find our dot product, P dot Q, which would be, again, the sum of the product. So -20 plus -4 plus 42. So is that 18?
Yeah.
So another meaningless number at this point. Again, skills now, context, underlying meaning. That comes later. All right, some properties of the dot product. All right, so anytime you throw some properties at some concept, it adds a little bit more meaning to it, because it's like, okay, we have a skill here, but if there are some known properties and theorems associated with those skills, that's good news, because that kind of it supports the idea of the importance of the concept itself. All right, so at minimum, we could use the commutative property, associative distributive properties, in conjunction with the dot product, which is great. But again, what are we using it for? We'll see. The property of magnitude is a big one. We'll see that in action in a couple of minutes. But below, you can see that there are just a couple of applications of these properties. All right, so I'll put some stars on these so that you can try them on your own, because it's really just a question of dot product in particular order. All right, so what am I doing here? I'm finding the dot product of A and B first, and then multiplying the results by C. All right, so here I'm finding the scalar product of an actual scalar and vector C first, and then taking that and multiplying it by A using the dot product. And then the third one, or number 5 in this case, is the magnitude of B squared, but the property of magnitude tells us that that's equivalent of the dot product, equivalent to the dot product of B in itself. All right, so it makes it a little bit simpler than actually finding the magnitude of B and then squaring it. In fact, let's take a minute right now and talk about this one, because as I flash through the review for the test, you might have seen that this is one of the possible proofs. All right, and you can see this is actually a nice one. It's not bad at all. All right, but it's in general terms. If we're working in 3 space, then I would establish V, vector V, as some unknown, completely unknown vector. All right, so I got to come up with some variables that represent the components. I'm going to keep it simple, relatively simple, and call it V1, V2, V3. Try to stay away from subscripts, but in this case it seems to make sense. It's vector V, first dimension, second dimension, third dimension. Right. You could do that too, either way. So in this case, if I want to find the product of V in itself, the dot product, I would be taking V1 and squaring it, adding to that V2 squared, and then adding to that V3 squared. All right, so that is the squared value of each component. But really, I mean, could I just square it? Well, I multiplied it by itself because it's the dot product of V and V. So V1 multiplied by itself, V2 multiplied by itself, and V3 multiplied by itself. That's pretty close to the magnitude formula. It's just it's missing a radical. All right, so let me introduce a radical. No, it's all good. No, it's not. Because I can't just introduce a radical. Unless I do what? Square it, right? A radical squared doesn't change the value of whatever it is you started with. Like the square, if I start off with a 2, slap a radical on it, it becomes radical 2. Square that, it goes back to being a 2. So it's equivalent. All right, so that's the same thing. But the thing that's contained in the parentheses, that's the definition of the magnitude of V squared. So inside is the magnitude of V, and we still have that leftover power of 2. So the dot product of V in itself is equal to the magnitude of V squared. All right, so that makes this an interchangeable operation. So it's all a matter of convenience. If I find it easier to figure out what the dot product is, then I can use that to figure out what the magnitude squared is. Right? If I just need the magnitude, right, so I find the dot product and then take the square root of the result. I no longer have to actually find components, use the Pythagorean relationship and things like that, right? Especially, I mean, in a sense, you're doing that anyway. But if I already have to find the dot product for some other reason, then I can use that information to go a little bit further with it. Right? So it's a pretty cool realization, I think. So I'm in the mood to invent formulas, so let's invent some more. Dot product of two vectors is the product of magnitude of each vector and the cosine of the angle between them. All right, so this looks like it comes out of nowhere. I'm sure it was explained to me back in the day. But essentially or eventually it became, all right, just memorize this and use it, I guess it'll be fine. But it's actually pretty cool. All right, so what we have here is a triangular relationship. It's the difference between two vectors. And we learned 2 classes ago, I think, that the difference between two vectors is really just the sum of two vectors where one of them is negative. All right, so if I have vector u and vector v, if I want to find v minus u, that would be the same as, let me just bring it in, negative u plus v. So I would just need the vector negative u, which would be the same vector as u, just going in the opposite direction. So freehand drawing. All right, an attempt at a freehand drawing anyway. Oh no? Typo bonus. That's for somebody. In that case, it would be shift diagram. What do you think? An inch? An inch to the right? Or what would that be? 2.54 centimeters for those of you who are not inch people. Right. So that would be my negative u. And so if I want to find the resultant, I would create a parallel to v. So again, freehand drawing. Make a nice parallelogram out of that. That's a nice looking parallelogram, I'll tell you that right now. And so this would be negative u plus v. And so all we're really doing is picking up that negative u plus v and putting it up over here because it would be congruent. Opposite sides in a parallelogram are congruent. We didn't have to go around the room for that one though. And so that closes the triangle. So now we have a triangle, which is wonderful. Why do we need a triangle for this? Well, if you have a triangle and that triangle has 3 known sides and an angle, you might choose to use the law of cosines. So c squared equals a squared plus b squared minus 2ab cosine c, or the other 2 possible variations. The key ingredient is that side c is opposite angle c. What's angle c? Well, it's the one that you know. All right. So the side that's opposite of angle theta, I'm going to go purple for that, is v minus u. All right. Now, v minus u is not a side. That's a vector. The magnitude of that is your side. So the magnitude of v minus u squared would be equal to, now a and b are interchangeable, so it doesn't matter. U then v or v then u. But they're still magnitudes. Magnitude of v minus u squared equals magnitude of u squared plus magnitude of v squared minus 2 times magnitude of u times the magnitude of v times cosine of theta. All right. These would all be scalar quantities. So it would be the ordinary definition of times, multiplication. However, we do have a relationship, the magnitude property from the previous page, that tells us that if you square a magnitude, the result is the dot product between the two corresponding vectors, all right? So, or the vector in itself. So in this case, on the left-hand side, I could say v minus, well, it would be parentheses because the whole thing, each part is a vector. We'll worry about the right-hand side in a minute, but the left-hand side is just distributive property. All right, so we would be taking the dot product between v and v. This is where notation becomes important. I mean, it's always important, but extra important, because v squared without a magnitude associated with it doesn't have meaning, because v is a vector. You can't square a vector. A vector is a directional ray. Really, what does v represent? Something, comma, something, comma, something else. All right, what are you squaring? The first part, the second part, all of it? What you can square is a magnitude. So in this context, when I'm multiplying, when I'm finding the dot product, it is the dot product between corresponding parts. But what we do with those dot products is what's going to define everything. So the outers would be negative u dot v, and we'll have two of those. So negative 2 dot u dot v then plus u dot u. All right. So going back to the magnitude property, if I have the dot product between two identical vectors, that's equal to the magnitude squared. So I'm still working on the left-hand side. Right-hand side, I'm leaving alone for now. So this is the magnitude of v squared minus 2 dot u dot v plus the magnitude of u squared. The right-hand side we could bring back into play. And then beautiful magic will happen. We have a common magnitude of v squared. We have a common magnitude of u squared. So left-hand side contains only negative 2 dot u dot v. Right-hand side, negative 2 magnitude u. Crappy handwriting, sorry. I mean, blanket apology for crappy handwriting, that's always the case, but extra crappy in this one instance. Common factor of negative 2 that can cancel. And there it is. U dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Consequence of that new rule, that beautiful new rule, is that now I have something that includes an angle. That angle is the angle between vectors u and v. So I now have a technique that would allow me to solve for the angle that separates two vectors. I could even solve this equation for cosine theta. Cosine of theta would be equal to the dot product of u and v over the magnitudes multiplied. Okay, so at a minimum, you have a formula. You can plug and chug the formula, but if you know where the formula comes from, it's something you never really have to study. Yeah. So for a question like number 6, it says find the angle between each pair of vectors. It's up to you. If you like IJK notation or the vector notation, the component form vector notation, either way is fine. I mean, they have the same parts, so what does it matter? You don't need to convert from one to the other in order to use these formulas. You just have to know the coefficients. So in the first problem, we'd be looking at cosine theta is equal to the dot product between these two vectors. So this first one would be what we'll call a vector u in our minds, I guess, and the other one would be vector v. So multiply and add on the fly. 1 times 2 is 2. 1 times -1 is -1. 1 times -3 is -3. Poor quality line. Fixing that immediately. Then we could sum that out in a sec, but the bottom would be the magnitudes of each. So the sum of the squared values under a radical. So we're going to have 2 of those. 1 squared plus 1 squared plus 1 squared is 3. So the square root of 3. 2 squared is 4. 1 squared is 1 plus 4 is 5. And then 9 squared. So 9 plus a 5 is 14. So on the top, we're talking -2.
Wait, why is it negative? Why is it 14?
4 plus 1 plus 9.
Squares.
So -2 on top, and then what is that, root 42 on the bottom? So to figure out my angle theta would be equal to the inverse cosine of -2 over the root of 42. Degree form is fine. There's not necessarily a requirement of radian versus degrees for this particular topic. Like for polars and things like that, that there would be an expectation that you go both ways, or be prepared to go both ways. But for this stuff, I think the focus is on getting a sense of the spatial aspects of it, and to kind of have to translate everything to radians, from radians to degrees into your own mind, or vice versa is a little iffy. So about 108 degrees roughly. So we now know that there's roughly 108 degrees separating vector u and v. All right, so we now have a technique that allows us to find the angle between the two vectors. All right, so the second problem here, number 7, is along those same lines. But it brings us to a concept called orthogonal vectors, which talks about the idea that the dot product is equal to 0. If the dot product between two vectors is equal to 0, then we call whatever those vectors are, whatever they're defining, the relationship to each other would be orthogonal. So then if we go back to our cosine formula, let's just kind of play this out for a second. If the dot product of u and v was equal to 0, what would the entire right-hand side of this equation be equivalent to? 0. What angle in the unit circle has cosine equal to 0? 90 and 270. But let's look at the 90, for example. 90 degrees separating two vectors would make them right angles to one another, right? Mm-hmm. All right. So in space, if any two vectors are right angles with one another, I don't know why I'm using a mouse. I need to use a finger. Then they're considered to be orthogonal. So we would say form a 90-degree angle. So it forms a 90-degree angle. The issue is, in two space, 90 degrees are very easy to identify. I mean, or at least something that's near 90 degrees. Maybe it's 89, maybe it's 87 degrees, 93 degrees. But when something looks like a right angle, it looks like a right angle. It's pretty obvious. In three space, it's a matter of orientation, because you could have two vectors that are pointing directly at you. If that's the case, if you're looking at them straight on, how do you know that these two vectors are going to form a 90-degree angle with one another? Right? You're probably not even going to be able to see this one if you're looking at it at the wrong angle, because all it's going to appear is as a point. And if you look at it like this, you're looking at one vector that might overlap with the other. Right? So there's no way to tell from this perspective that they're orthogonal. It isn't until you turn them that you can see whether they are or they aren't. Right? So then how do you figure it out? Well, you figure it out by determining the dot product. And fun fact, it's really easy, because the dot product is just multiplying components and adding them. So this goes right back to the skill on the previous page. 10 plus 0 plus negative 10, you get a result of 0. Therefore, they're orthogonal. Fun fact, the symbol for perpendicular in two space is also the symbol for orthogonal in three space. All right. So if you didn't know that, this means orthogonal. Also, fun fact, perpendicular is a special type of orthogonality. Okay, so when you were learning about perpendicular lines, you were actually learning about orthogonal lines in two space. The perpendicular case is the two-dimensional case of orthogonality. All right, so a little bit of trivia there for you. Any space. Yeah. As long as they form a right angle with one another. All right, so 8, 9, and 10 are along the same lines. So V and I, V and J, V and K. Just to touch on it for a sec here, vector V is given. I is the vector 1, 0, 0. Now we're in three space, so it's 1, 0, 0. If we're in two space, it's 1, 0. You know, so it all is relative. J is 0, 1, 0. This is all typed out for you a couple pages ago, but sometimes you need to hear it be said. 0, 0, 1. Sector 0, 0, 1.
Is I or I hat?
You can go either way. The proper way to do it is with a hat, but I'm not drawing little hats every single time.
Plus you wrote it in bold.
And I wrote it in bold, exactly. Exactly. All right, so the last thing that we're going to talk about tonight is projections and components. All right, so what you can do is project one vector upon another, or find a component of one vector acting in the direction of another. This was along the lines of that, I think it was Tabitha's blimp from earlier, where the wind was supporting her movement. And it's a question of, well, it's not entirely supporting her movement, it's in part supporting her movement. You know, so if you had, well, I mean, that's really what it is. I mean, I could go with a current in the water, but wind in the air is the same idea. I mean, if it's not blowing against you in any way, shape, or form, then it's probably supporting you. So if the flow is in your direction in any capacity, so even if it's like 1 degree in your direction, it's still going to support your movement. It's not acting against you. It may not be supporting you very much, but there is some support there. So what we want to do is we want to figure out how much of a support from one vector would impact another. All right, so that's where the projection component stuff comes into play. All right, so vector projection on V onto U is vector labeled. Of course, we have to come up with this funky notation here. Proj vector projection. We couldn't come up with anything better than that. I scoured textbooks. I've looked at, I've asked. I've gone through every source of media that I could find, and yeah, everybody uses proj and comp for projection and component. It's like, couldn't just create a symbol for it? I mean, you use hats and bars and things like that for everything else. I mean, you just seem to make it up on the fly. Use Greek letters for things when they don't need to be used, but for some reason we gotta go with proj. All right, so this is the vector projection of v onto u. All right, so it is the same initial point as u and v, and the same direction as u, represents the component of v that acts in a direction of u. I mean, there's a lot of words here, but I'll get into the specifics of it in a minute. All right, if theta is the angle between them, that's the important piece. By properties of triangles, so this is like by saying, by an entire course of geometry, we know that this is a true sentence. All right, well, yeah, well, maybe some of us do, I guess. But do we really? I don't know. We'll find out in a minute. When expressing cosine in terms of a dot product, this becomes all of this stuff. But this, I wouldn't let it slide if I were you. Like, yeah, oh, by math magic, we have this relationship. You're like, okay, cool. Yeah, all right, magic wand, awesome. That's a great explanation. All right, so let's get into the diagram here. We have some angle theta. We have a vector v that has a magnitude. We don't know what that magnitude is, but it's there. We also have a right triangle. Now, this didn't come standard equipped with a right triangle. I dropped an altitude to make it a right triangle, right? Because what I'm looking for is the impact that V is having on U. So think of V as the wind and U as Tabitha's blimp, all right? So V is supporting the blimp in some capacity, we just don't know how much. So what we want to do is figure out, okay, if I took the component of V that's acting in the direction of U, what would that look like? And so that would end up being some distance, because vector distance represents its magnitude. I don't know how long it is, so I just ballparked it, and then drop an altitude, creating a right triangle. But that gives us the opportunity to use right triangle relationships. All right, so for example, I know the adjacent side of a triangle and the hypotenuse, so I can say the cosine of theta is equal to the adjacent over the hypotenuse. All right, so if you compare this to that, we're kind of there. So one thing to consider, again, is that if I call something a vector, you can't perform an operation on it. I can't just like square it or do something along those lines. Right? It's only the magnitude that I can work with. So if I know the magnitude of this projection, then I can actually divide it by the magnitude of vector v, and that would give me the cosine of theta. But more importantly, it tells us through cross multiplication that the magnitude of the projection would be equal to the magnitude of v multiplied by the cosine of theta. So the magnitude of v onto u, all right, so the thing to keep in mind is, again, v has some component that's acting in the direction of u. That is the projection. The notation's a little weird, but if you're always thinking about the subscript as being the vector that you're acting on, then that's probably the way to go. All right, so it's kind of like the notation is on the u, like it's not quite a denominator, but it's below everything else. people have said that this has helped them in the past to remember. And it's like, the notation has it on the U, so we're actually projecting on the U, right? So the U is the subscript that's below everything else. So if you don't like it, I'm sure you'll figure out something else, but that's what I got in terms of mnemonic devices. So what we define, the component of V acting in the direction of U is the magnitude of the projection, right? So the projection is the vector quantity, right? So it's got components, right? It's got an x value, y value, z value, and it's going off into space. The magnitude of that is known as the component, all right? So that relationship corresponds with all this stuff. So how did I get to this? Well, we do have a relationship involving the cosine of theta. We just figured that out.
I know that.
Yeah, cosine of theta is this. So clean it up, magnitudes of V will cancel out, and so you get a nice little shortcut rule to help us figure out the magnitude of the projection, which is the same as the component, dot product over the magnitude of U. All right, nice and easy in terms of the calculation. Derivation, a little bit out there, but in terms of once you have this formula, performing a calculation, not too bad, all right? And again, I mean, not that you need me to explain this too much, but why do I ask you to derive some things on a test? Why do I give you a problem to derive? Well, if I don't, then this becomes an exercise in you reading a formula off your note card, plugging numbers in and getting answers. I don't know that you truly know the stuff that way. I don't know if you truly know the stuff by deriving formulas either, but I'm more inclined to believe that you have a better sense of the underlying concepts by deriving the formulas than just by rote calculation. All right? It's a personal philosophy. Not everybody agrees with it, but it's me. So U dot V over U, if you're looking for the magnitude of the projection. All right, movie reference? Yeah, very good.
What was it?
Return of the Jedi.
Oh.
Start with Star Wars and work your way out from there. And you can always...
Which episode? The first one before
Return of the Jedi. ROTJ. All right, so on the next page, we have some examples that talk about finding the projection of V onto U. If we multiply the projection by a unit vector, we can get a brand new formula, but that formula is really just the projection multiplied by a unit vector. So you have to be specifically asked to find a unit vector that represents the projection of V onto U. All right, so it's a very specific type of question, but you'll see that going forward. All right, so anyway, these problems, it's really just relying on a formula. If you need to find the actual vector itself, then you would multiply it by a unit vector. So let me take you through one and then we'll call it a night. So I made it a trick question on a test one year, and I can't remember if I changed it from being a trick question. So be prepared for the possibility that a question on the test could say find the projection of U onto V. All right, so same setup, except it would be the magnitude of V on the bottom. All right, so. And I would totally consider changing it, except I think I'll totally forget to change it. So U dot V, so we're looking at -3 plus 20 plus 3. That's something. It's a nice 20. Take it. All right. The magnitude of u. All right, so that's the square root of 1 squared, which is 1, 4 squared is 16, and then 3 squared is 9. All right, so we have 20 over the root of 26. I wanted it to be 25, but alas, that is not the case. All right, so what they're asking us for here is the projection of V onto U. All right, so we were able to come up with the magnitude of the projection, but I actually want the projection itself. All right, so what I need to do is figure out what that would be if it were multiplied by a unit vector in the direction of U. All right, because we are going on to specifically U. All right, so if you look at the formula, I mean, I went through the full-blown derivation here. For some reason, I opted to type this one out, but none of the other ones, I don't know what's wrong with me sometimes. But this first part here, the magnitude of V multiplied by U dot V over the two magnitudes multiplied, that's the magnitude of the projection. That's just a continuation. The other part is just the unit vector U. Right? So all I'm going to do is multiply this by U over the magnitude of U. All right, because I talked about this when we talked about unit vectors. What a unit vector does is it defines your system, just like units define a scale on an XY axis. You go by ones, you go by tens, whatever. Whatever you go by defines your scale. Right? Your unit vector defines really essentially one of whatever the vector is, one unit of your vector. All right, so if I know that this is amounting to 1 unit of that vector, then I multiply it by my desired magnitude, then I have the overall vector vector including the desired magnitude. All right, so this would be, I need a marker, equal, we have 2 over root 26. We have the magnitude of U, we already figured that out. So I'm going to multiply it by U divided by each part of U divided by that magnitude, right? Because the bottom of my component formula was the magnitude of U. So I'm going to take each one of these bad boys and divide by the square root of 26. All right? You could. All right, so clean it up. Negative 20 over 26. Simplify it in a second. Or simplify on the fly if you want. 80 over 26. 60 over 26. And so the projection of V onto U, so the amount of V that impacts U, so in the direction of U, was 20 over root 26. That was the magnitude of that. But if I were to go out in terms of a vector in the direction of U, this is how far I would get. All right, so negative 10 over 13, 40 over 13, 30 over 13. Decimal form might be more relatable just to get a sense of the scale. But we're talking less than 1, a little bit more than 3, a little bit less than 3, or between 2 and 3. So it gives you a little bit more sense of scale.
Is it all right to leave it as like 20 over 26 times negative 1, comma 4, comma 3? Like with a scalar removed?
Yeah, it depends on the instructions.
Okay.
Yeah, just be careful of that. But generally, once you got to really this point here, you've essentially demonstrated the skill. So at that point, you're probably okay. All right, so a star for the next question, and then we'll pick up with the cross product next class, and then that's it. So you want to be taking time. You know, I saw all these problems are all well and good, but the best preparation for a test is the review problem set. There's a bunch of problems there. It goes through the entire unit. It's as you know, I mean, you don't need me to tell you, it's a lengthy unit. They're all lengthy units. So work through that before next class so that at the end of class, if you have questions, you can ask. All right.